Hello, everyone. This class, we're going to continue with our computational methods in engineering, and specifically, we're going to talk about symbolic mathematics. So if we do a quick recap of last class we mainly discussed different types of data in MATLAB, right? So we mentioned that there are, in terms of number, we can have the double precision, single precision, and then integers. For integers, there can be different number of bits for storing the integers, right? But if you directly use the integer, for example, assigning the a value with a value of 1, and then it's the automatic or the default format is going to be double, right? Double precision. So then we talked about the characters, the strings, numeric, right? Numeric basically include the integer and basically the single precision or double precision float numbers, right? So there's logic array, duration array, date time array, right? How we can convert numbers into dates, right? And then if we combine different types of the array, different types of the data, then we can create a cell or create a structure, and eventually it's a table, right? Table is sort of similar to the structure array. Okay. So this class we're going to talk about the symbolic mathematics, right? The symbolic toolbox is actually quite helpful for us to conduct calculation using symbols, right? As it indicates here. So we can basically do simple differentiation or integration, or do, for example, create polynomial equations or do simple plots, right? So it allows you to enter expression in symbolic form with symbolic data types, right? Expand or simplify symbolic expressions, find the symbolic roots, limits, minima, maxima, so on, right? Differentiate and integrate the functions, generate Taylor series of functions, right? And some other tools, right? So basically, there can be different applications of the symbolic, basically the symbolic toolbox, okay? So to create these symbolic variables, right? So it's actually quite easy. We just need to define certain variable to be a symbol, because if you recall, we could only pass certain value as certain value to a variable or string to a variable, right? So what if we want to create an expression, for example, y equals a multiplied by x to the power of 2 plus b multiplied by x plus c, right? So then it's not going to work because we have not defined all of these symbols yet, right? So we cannot do integration directly with this symbolic form, right? So then basically we can use the symbolic toolbox, right, to create or to sort of facilitate some of these calculations. So basically now if I create a new file, let's see, class 13, right? So the first is creating symbolic variables, right? So then what we can do is we can just type in sims, right? Sims, now you can specify what type of symbols you want to define. For example, A, B, and C, right? And then now you can start to define sort of the symbolic expression. You can pass the expression of A multiplied by x squared plus B multiplied by x plus C, right? And then if you do, let's say we run this section, right? Control plus enter, right? So we can run this section. And then now you can see that basically here we define all of these symbols, and then the y here is our expression. Okay, so this is how we can define symbols. And then basically, if you want, you can also define, for example, y1 being this form and y2 being, let's say, we just do this form, 2x plus 1, right? You can do y2 being x to the power of 2, or x equals, y2 equals 4x plus 3. Right? And then you can calculate y3 equal y1 plus y2. Right? So if you run this again, Okay, we didn't define y1 and y2, y2, y3. Okay, so if you run again, here you can multiply, right? So now you can directly see that, well, we calculate the right thing, right? Y1 is this, y2 is 4x plus 3, y3 is basically they combine together and directly get the result, right? This is sort of like the hand calculation. You have certain expression and then you add them together, and this is what you get, okay? So we could also define whichever type of symbols we want, right? So let's see, we create another, yeah, this is still the same thing. We can basically add more variables here, right? For example, k, p, p0, right? So we can define, let's say, yeah, so we can define these parameters and think of some combinations, right? So for example, p equals p0 multiplied by exponential k multiplied by p, k multiplied by t, right? So then you can define or not define the p, right? Because p basically you pass the variable over here. So theoretically, you don't need to define y2 or y3, right? You don't even need to define y1 because these x values, these are already sufficient, right? So if you run again, right, or you CLC, clear CLC, right? So this is what we get. Okay, y1, y2, and y3. So one difference actually is that you can tell whether that's symbolic mathematics or number is you can try giving, let's say, y with a value of 2, right? So now this is not symbolic, right? This is just a variable. So if you run it, you can see that y equals 2, the 2 is over here. So basically, there is an indentation, right? But if it's symbolic, you directly start from the beginning of the following line. So this is sort of one difference when you are doing symbolic mathematics or when you're using, let's say, directly the variable or the default data type in the MATLAB, right? So this difference indicates whether that's a symbolic expression or not, or it's just a numerical, right? So we created this symbolic expression. We could also create symbolic equations. So I mean, this is another way here. This is another way to define the symbolic variable. So for example, we didn't define M or C, right? So you could directly use sim and then M multiplied by C to the power of 2. Okay, so if you run this, string to symbolic. Okay, so I guess this is a version of the MATLAB issue, so we don't have to use that. So let's do this, str2 sim. Okay, so now you see that we also passed the equation of E equals MC squared to the variable E here, right? But the difference is that we don't have M and C predefined in the let's say the symbolic variables. Okay. So next we could also create equations. So instead of the impression, right? So these are impressions, right? Y1 equals something. We basically pass the impression to Y1. But we could also create an equation. What that means is that we could creating symbolic equations, right? So sims, let's do the same thing. Clear CLC, sims PVNRT, right? So then we can define ideal gas law equals PV, P multiplied by V. And then here to define an equation, we will use double equal sign, right? N multiplied by R multiplied by T. Okay. So if we just execute this section here, right? You could type in Control Enter, right, to run this current section. So yeah, basically this is our equation. The ideal gas law. If you check the ideal gas law, now it's has a symbolic format, right? The data format is symbolic, and then it has the equation PV equals nRT over here, right? So this is how we can define a symbolic equation. So you may wonder, what is the use of this, right? So using MATLAB as a calculator is already quite helpful. Why do we need to define these symbolic equations? So later on, I'll show you how the symbolic toolbox can help us simplify or to solve certain symbolic equations. Okay, so here are some practice, right? So a symbolic expression. So basically we can do hands on, right? And then we can copy these terms inside, right? So then basically these are symbolic expressions. You have x squared plus 1x squared plus 2x plus 2. And then if you execute this section, you can see that the x squares are combined together, okay? So you could also try this, okay? Minus b, and then you put the terms in the bracket, right? So now instead of having the expressions directly outside, we could actually put a bracket over here, a parenthesis, and see what we get, right? So this is the first one, this is the second one, right? And then let's just remove this right now and then execute. Well, it still works, it's the same, but then let's try this one. Okay, so x1 equals minus b plus this whole term, and then, yeah, if you run this, basically run this section here, you will see that the minus b terms are not merged together, right? And also we know that this term actually will cancel each other. But then in terms of the result, it seems like the addition here is not considering the simplification or helping us rearrange this expression here. Theoretically, if we just write it on paper, we know that these two terms will cancel out because these are the quadratic solution for a second order linear equation, right? Not second order nonlinear equation, polynomial equation. Okay, so it looks like the symbolic expression is not able to help us simplify certain expressions. Okay, so the same thing, we can try putting this expression here. So y1 equals x plus 1 to the power of 2, and then here. So if you write these two together, you would actually know that if you expand this term, right? So that's x squared 2x plus 1. And then theoretically, if you minus these two terms, then you're going to get 0, right? But if you run it, you can see that y3 is actually still the same term here, right? It's just rewriting some of the sequence here, but it's not helping us sort of simplify this expression, right? So under this situation, what do we do, right? So we can use this simplify function in the symbolic mathematics toolbox of the MATLAB. So what you can do is you can just type in, right, instead of x1 plus x2, you type in simplify x1 plus x2. Okay, so the same thing over here, simplify. Okay, run it. Simplify. Okay, so now you see we actually got this term basically simplified, right? So if you check x3, right, x3 here is these two terms gets canceled, and then you just have b minus b over a, right? So then the same thing, y1 or y3 equals y2 minus y1, you'll get 0, right? So this is how we can ask the symbolic toolbox to help us simplify these symbolic expressions, right? So actually, in terms of manipulating these symbolic expressions, there are quite many functions to help us do these, I would say, tedious tasks. So for example, you could use the expand function. Right, so hands-on, this is simplify, right? You can use the expand function. So what it does is that if you see, we originally defined y1 being this term, right? So we could just expand and say y1 now equals expand. Let's see, define it y11 as y1. Okay, so if you run this section, you see that all the terms are expanded within the parentheses, right? You can also try higher order. For example, now y4 equals x plus 1 plus y, right? Plus z to the power, let's see, to the power 3. The only thing is that we have to define the symbols, right? Sims x, y, z. Okay. And then expand y4. Let's define this as y5, right? So then if you run this section, you see that y4 is equal to x plus y plus z to the power of 3, and then y5 is just the whole terms, right? So you can see that actually this symbolic toolbox is quite helpful when you're dealing with symbols or dealing with symbolic expressions. It can help us expand the terms in the parentheses. It can help us basically cancel certain terms, right? And then can help you simplify the terms on the left-hand side or right-hand side. Okay, so if you have a sophisticated equation. Okay, so then the next is a factor function, right? So for example, you have an expanded term of the function, right? Since x, y equals x to the power of 3. Let's just copy everything over here. And then this is an expanded, that's a polynomial, sort of a polynomial equation with single variable. And then we could just factor y. So if you do that, it can help you identify what are the factors inside this equation. So it's x1, x1, and x1, which means that it's just x plus 1, x plus 1, and x plus 1, which means it's just x plus 1 to the power of 3, right? So you could also try this, right? So then y5, because we already defined sort of y5 over here, right? So you can try y5. So you can see that it's x plus y plus z. It's very convenient, right? Because initially, if you just directly have the expression over here, you don't know what this means, right? Unless you really memorize the terms inside or the expansion of these polynomial equations, right? But then MATLAB can help you identify the factors in these equations, and then it can help you simplify the equation. And then the next is the collect. It's a collect function. So what the collect function does is it's going to help us rearrange the function based on the terms in front of the different variables. So for example, if you have a function that looks like this, right? X to the power 3, and then 3 multiplied by x to the power 2, y, and so on and so forth. You can see that it actually started from the highest order for y here, for x here, right? So what if you want to rearrange the equation so that it starts from the term of y, for example, y to the power of 3, and then the next term is y to the power of 2 multiplied by something, or y to the power of, for example, here, these two terms can also get combined, right? So you can rearrange the equation based on the certain variable, right? And rank them based on the order. So this is what the collect function does. So for example, you can try to do collect, right? So right now we have y5, right? The y5 variable, and then we can run it based on the x. So you run it, you can see that we're arranging it based on the order of the x, right? So x to the power 3, x to the power 2, x to the power 1, and then these are sort of the rest variables that has the x to the power 0. So you can also rearrange it based on y, right? And then let's see, based on the order of z. Okay, so this is Z, right? Based on the order of Z, right? So let me see what is going on with Y here, basically. Oh yeah, because we define X and Y in a different way. So let's just redefine X, Y. So actually the best way to do this is to include um, the clear and CLC in every section. So it does not carry the memory for the previous, from the previous section, okay? So if you, okay, so we need to define Y5 being here, okay? So Y5 is X plus Y plus Z to the power of 3. Right. So then you can also do the same for the Y here. And now you see that it's arranging this polynomial equation um, based on the order of Y. Okay, so this is a collect. And then the next is the poly to sim function. So as the name suggests, it's converting the polynomial equation into a symbolic polynomial equation to a symbolic expression. So what it does is that, for example, if you define A being, let's say, 1, 2, and 3, and then you can do sims X and Y. So Y equals poly to sim, right? So it starts from A and then X. Let's run this, right? So basically it fits these polynomial terms, right, to the different order of X. It starts from the order of 0. So 3 multiply X to the power of 0, 2 multiply the X to the power of 1, and then 1 multiply X to the power of 2. So this is how you generate a polynomial equation, right, relatively simply. Okay, so just as a review here, the simplify command basically use this algorithm to simplify each part of the expression. So for example, if you have the term over here, and then if you simplify it, you can get the complete, for example, the complete expression, just disassemble, right? You have different terms over here. And then you could also, there's the expand, right? So the expand function, it can help you expand expression. And then let me see, we didn't define this numerator, but it can expand the parameters inside the brackets, right? So the factor, the same thing, the factor will find out the factors inside this sort of the polynomial equation, and then basically return you the different factors of this polynomial equation. And then the next is the poly to sim, right? Poly to sim, we said that we can just put in the numbers and then create the we don't even need to define the x here, but let's say if you want to create a polynomial equation that's based on z, right? So you create y equals a and everything to z here, right? So then you could also do the sim to poly function, right? So sim to poly function. And so basically what that means is that you can have a bunch of parameters, like an expanded function, right, to the power of 5, for example, and then a multiplied by x to the power of 3 plus 1, right? And then you can run this poly to sim function for y, okay? So if you run it, polynomial has more than one symbolic variable. So we cannot have more than one. So let's just put a 4 over here, right? So it looks like it has to be numeric, right? So then if you run it, then it has basically 6 terms. So we start from the power of 0, right? The order of 0, 1, 2, 3, right? 4, 5. Okay, so it returns this symbolic term. Let's say it's not a symbolic term, but let's pass it to the variable b, right? So then it basically will return you this array here that contains these different numbers in front of the different orders of x. Okay, so a pretty interesting function or helpful function is the solve function. So the solve function will sets a certain expression to 0 and then solve the equation. So the most common sort of solution for a function, for example, solve function, right? Since x, y, let's just do the clear CLC again. I always forget about these. Okay. The most common sort of expression, right? So we know that it's a second order polynomial equation, which is y equals a multiplied by the x to the power of 2 plus b multiplied by x plus c, right? So what is the solution to this function? Right, so we sort of showed earlier, right? x1 equals this, x2 equals this, minus b plus square root of b squared minus 2ac, and then divide by 2a, right? So actually with the symbolic mathematics toolbox in MATLAB, you don't need to memorize that anymore. So you can just solve y. Okay, so this is the result. Minus b plus square root b squared minus 2ac divided by 2a, right? You also have the two solutions over here. Okay, so then you may wonder, well, what if I have this function here? I just want to solve for a. I'm not interested in x, right? I want to solve for a. So then it should be basically setting this equation to 0, and then it will be minus bx minus c divided by x squared. So how do we do that? We just need to add an a over here. Okay, so let me just start from a new line. Solve ya, right? So the a here is sort of the variable or the unknown that you want to solve for, right? So basically set this equation to 0 and then you can solve it, okay? So remember earlier we defined a function of, let's see, the p equals p0, right? Exponential kt, right? So let's see over here. It doesn't limit the solution to the polynomial function. You can also try, for example, the exponential equations. So p0, k, p, also do p. Okay, so to do that, we have to sort of rearrange this equation. We have to minus p, right? So we need to define a new parameter. For example, again, let's use y here, right? And then solve, for example, by setting it to be 0, we want to solve for what is the temperature, right? So then let's solve u 0, and we need to solve for y, right? So you can see that basically you set this y to be 0, and then basically these two terms equals each other, and you take the log and then divide by k. This is a solution. So you can see that the solve function can be quite helpful. But then the thing is that the equation has to have a solution, right? It has to have an analytical solution. So what if it doesn't have an analytical solution? So for example, we can have higher orders, right? For example, x to the power of 5, and then here x to the power of 4. So can we still find a solution for y? Y, x, right? So it's say that to the power of 4. Right? So then you can see that it's just going to return you this thing, root of something, right? It doesn't have a analytical solution. So for the ones that doesn't have an analytical solution, it's just going to basically rephrase this equation and then say that it has 5 roots, right? Because it's to the power of 5, right? So let's try if we have a third order equation, right? Even third order equation, you don't have a solution. Only second order equation you have a solution here, right? So you can see that basically the solve function is sort of limited. It's not the same, or it's not as powerful compared to the f0 or f solve function that we showed earlier. But the difference is that the solve function work with symbols, right? F solve work with numerical terms, right? So basically you have to define the function. We said that f solve function use iteration, but here if you have symbols, you don't even know the numbers. There's no way that you can use iteration. The function use iteration to solve the problem. Okay. So yeah, this is a hands-on example, right? We already did it earlier. We can also try this one. So that when you solve the function, it doesn't have to, let's say, you don't have to, let's say, we can go back, right? You don't always have to create a new function to make it zero. So what you can do is you can just define an equation. So equation equals p equal this term. So remember earlier we said that we could have symbolic expression and symbolic equation, right? So here we're defining this symbolic equation. So then you can just solve for equation and then solve for t. Okay, so you're going to get the same thing, right? You define, instead of defining an expression, you can define an equation and make the equation to work and then solve for t. Okay, so this is what it means by the second example. Okay, so yeah, as we showed earlier, by specifying the solve function to be respect to a, right? So you could also solve for the expression of a by making this term to be zero, right? So this is what you're going to get. Okay, so with the solve function, you could also solve for systems of equations. So this is sort of linear, similar to the linear algebra that we talked about earlier, right? So then we can do systems of equations, right? So you could actually define symbols, right? X, Y, and Z, right? So we can define 1 being the equation of 3 multiplied by X plus 2 multiplied by Y minus Z equals 10, right? So this is our first equation, second equation, third equation, 2, 3. So it's minus X 3Y plus 2 multiplied by Z equals 5 minus 1 X Y minus Z equals minus 1. So we define our 3 functions, right? And then you could do X, Y, Z equals solve 1, 2, and 3. Okay, so basically you can solve these systems of equations. Okay, so you can see that this is basically for different sets of linear equations, we have different solutions. Okay, so actually we can try, right? So we can try just having 2 equations and see what will happen. All right, so basically it's going to predefine a certain parameter to be 0 and then solve the rest. Okay, so it can be used for solving, let's say, the underdefined problem. What about we have overdefined problem? It's y is z equals 0. Okay, let's see the. So theoretically, it should be minus 3, right? So let's make it minus 2. So can we solve for 4 equations like an overdefined, right? So if it's overdefined, you cannot find a solution. Okay, so basically the systems of equations, by using a symbolic calculation, you can only solve or calculate underdefined or exactly defined. sets of equations. We cannot solve overdefined equations. Okay, so the note here is that the solve function will give you the symbolic output, right? So basically you can change it to, right, change it to the actual value, because if you see the solution here, these are still symbols, right? So you can use a double, right, to convert it into numbers. And then the other thing is that for these, the solve function is actually, we said we compared the linear algebra, like the matrix calculation method or the fsolve or the solve. So overall, still the linear algebra method, which is a matrix method, is still the fastest, right, compared to these different forms. For the solve function, you can imagine, because we're using symbols to solve the equation, so it's going to take a longer time. Okay, so the subs function, it can let us basically substitute certain variables. For example, if you define a quadratic equation being this way, right? So if you do the subs function, then you're going to substitute x value by the y, right? The x symbol by y. So you can substitute the equation here. So let's see, you can define substitution. Okay, add a clear and CLC. Okay, so sims A, B, C, X, Y. Okay, so we said that Y equals A multiplied by X to the power 2 plus B multiplied by X plus C. Okay, all right, quadratic. So if we define a new quadratic equation, then we do subs quadratic X with Y. Okay, so this is Y quadratic. You could also substitute certain variables with numbers. Okay, so what you do is you can substitute, let's say, X with the value of 2, right? So this is your solution. Okay, so, or if you already know what are the values for A, B, and C, and X, right? So you could do subs, okay, quadratic. And then here, note that these are symbols. So we're going to use the curly bracket with the values in curly bracket as shown over here. Okay, this is a substitution. You can do multiple substitution as well. So this is multiple substitution. Okay, so then there are easy ways to make plots, as the function indicates. You can do easy plot. So you can, for example, define x at y, and define y equals 2 multiplied by x to the power of 2 minus 10. Okay, so then you can just do easy plot y. So we're getting this function here. You even have the title over here, right? And typically it's just going to give you the range from -6, or give you the range of that's showing you sort of the range of the parameter. Okay, so you can also change the limit. So you can do x lim, let's say -10 to 10. Okay. Yeah, it looks like it's just giving you the range of somewhere around minus to +6, right? So let me check if we change it to 2 here, see if the x-axis change. It doesn't change, okay? So yeah, basically this is a predefined range for you to plot the function, okay? But if you want to have the entire range of the function, then it's basically better, or let me see, easy plot. Function A and B. Okay, so we can specify the range. right? So let's say we specified from 0 to 5. Okay, so yeah, we could plot this function with specified range. So this is an easier way to make the plot, right? And then let's see if we can select the value, right? You see that it has pretty fine x values, right? So you can select whatever value you want. Okay, so the next is the differentiation. So we said that the symbolic toolbox is very helpful when we're trying to work with symbolic expressions or symbolic equations, right? So you don't have to hand derive the derivative for the functions anymore. So you can directly use these differentiation or integration functions to do your calculation, right? So then it's just a diff function. So for example, you can define f, right, sims x and y, right, and y being still the ax plus bx plus c, right? So you could define a, b, c, right? So you could just directly do diff y, x, okay? Right, this is correct, 2ax plus b, okay? And then you can also do sine x, right? And then exponential of x, right? It's log of x. You can add whatever function you want, as long as it has a sort of the analytical differentiation result, right? So we know that some equations, they don't have differentiation results. So, but here you can see that we get everything, right? So you can also differentiate based on different variable. If you don't have anything, right, if you directly do y, and then it's going to treat x as a variable. But let's say that if you want to take the derivative with respect of a, right, so then it's just x squared, right, because there's no a terms for the rest of the terms, right? So basically, this is how you can take the differentiation. And then if you don't put the order, right? So basically, if you just directly use the diff, then it's going to only take the first order of differentiation, right? Diff, let's say y, x, 1, right? These two are going to be the same. But if you take the second order differentiation, right, then this is what you're going to have. Okay, you can take, let's say, 10th order of differentiation, right? So this is going to be the result, right? So you can also do integration. So you can do a lot of calculation with the symbolic toolbox here. So as long as, again, as long as they have analytical solutions, right? So then, for example, you have the y already defined over there. So you can do int y x, right? So let's see, redefine y over here. Okay. So if you do the integration, this is the integral. Okay, so you can also define the range for the integration, right? So it can be 1, 2, right? So x being in the range of 1 to 2, right? Or if you just want to include for example, a constant, right? So you can also just do, let's say, a, b, or x, or m and n, right? Basically integrate between the range of m and n. Right? You can also do the integration. Okay, but again, we need to make sure that the function has a analytical solution or analytical result for the integration. We know that if it's has terms of log or exponential, right? The integral, right here is 1 over x. But what if you have a integral of exponential to the power of 2, right? So how do you integrate exponential x squared? It's likely that we don't have an integral analytical solution, right? So let's try. So we'll do this way. Right, so it's going to include an error function, right? So what if we have sine, of x, right? So then it's just going to be int, right? You see the result is just int of something here, right? So it's not going to do the calculation anymore because here the integral doesn't have an analytical expression, okay? So yeah, because of that, there are limitations. So if that happens, we have to use numerical integration. We're going to talk about numerical integration and numerical differentiation in our next class and in our future classes. Okay, so we could also include an integration constant because we know that theoretically the integral of certain terms, you need to consider the constants, right? So then to include the constant, you just add this additional constant in front of the x. So what I mean is that if you have, let's say, y equals x, right? So we know that the integration of y over with respect to x should be half 1/2 multiplied by x squared plus a constant, right? But here, if you see, if we don't consider the constant, it's just this term here. But theoretically, there should be a constant, right? So then we can include any constant. It can be a, it can be x. But then now, if you do the integration, it has this constant over here, because theoretically, this term, if you take the first order of differentiation, that's x, right? Because this is constant. If you take the differentiation, that's 0. Okay. So some exercise here due to the time limit, we'll skip that. But now you can see that to solve for a set of linear equations, we have multiple tools now. We can use the fsolve, we can use the matrix method, and now we can even use the symbolic method. So here, for example, if you have a velocity, right, with some symbols here, you could calculate the distance, right? It's just the integral with respect to time. Okay, and then the integral is between 1 and 5, right? So you can also calculate the differentiation of velocity to find the the velocity, to find the acceleration, and then use the subs function to calculate the acceleration, right? So as a summary here, this class we learned about the symbolic mathematics in MATLAB. We can create different expressions. We can create functions, right? We can manipulate these expressions using functions such as expand, factor, collect, simplify, poly2sim, and then solve subs, right? Plotting, easy plot. We can do differentiation, right? We can also do integration, okay? So here it has the prime over here, mainly because if you don't define the x values in the symbols, then you have to include that. If you have already defined, you don't need these primes over here, okay? So that's it for this class, and let me know if you have any questions. Thank you.